Hi, my name is Shreyansh. This is my submission for the GPU specialization capstone project. The objective of this project was to architect and implement a high performance image processing application using CUDA C++. Specifically, I have built a parallelized 2D image convolution filter. While this operation is pretty standard on a CPU, it becomes computationally expensive as image resolution scales. This is something I've experienced myself in the past. My goal was to offload this heavy compute task to the GPU, leveraging thousands of concurrent threads to process pixels in parallel. Let's look at the project architecture. A key requirement for the assignment was a robust production ready code. Firstly, you can see I've included a make file. This ensures the build process is reproducible. I'm using the NVCC compiler with the O3 flag. Crucially, I had to target the specific GPU architecture available in my Colab environment. I used the ARC SM75 flag to explicitly target Tesla T4 GPU, which resolved runtime compatibility issues I encountered during early testing. Moving on, this is the main.cu file. The core of my solution is this processing kernel. I choose to map the problem to a 2D grid of thread blocks. You can see here that I calculate the unique global x and y coordinates for every thread using block IDX, block dim, and thread IDX. This allows every thread to identify exactly which pixel it is responsible for. A major challenge is the boundary condition. If a pixel of the image, its neighbors might not exist. I handled this with a defensive if statement here. If a neighbor in bounds, I ignore it, effectively applying zero padding to the image edges. In the host code, I prioritized memory safety. I am using CUDA malloc to allocate linear memory on the device. You'll notice I wrap my CUDA calls in a custom macro called GPU error check. In GPU programming, errors are often asynchronous and silent. This macro focus forces the runtime to report errors immediately, which was instrumental in debugging the kernel during development. Finally, the code supports command line arguments. It doesn't use hardcode paths. It accepts input files, output files, and dimensions dynamically via flags. Now, how do we know it actually works? I utilized test-driven development approach as I often do in my personal projects. Before writing the C++ kernel, I wrote this Python script. It serves two purposes. It acts as a data generator creating random binary inputs. It acts as the ground truth. I use the scipy.signal library to perform the exact same convolution on the CPU. The script then compares the binary output from my CUDA kernel sci-fi result byte by byte to ensure mathematical correctness. Here is the proof of the execution. I ran the solution on a 1024 by 1024 pixel image. As you can see, the kernel execution time was 0.18 milliseconds. This demonstrates the massive throughput advantage of the GPU. Most importantly, look at the verification log. Success output matches ground truth. This confirms that my parallel implementation produces identical results to the sequential CPU version, but with significantly higher performance. To conclude, I would like to mention future improvements. While this global memory implementation is functional, it is bandwidth limited. The next logical step would be to implement shared memory tiling. By loading the pixel neighborhood in the GPUs on chip shared memory, we could drastically reduce global memory traffic and likely double the performance. Thank you for your time and for reviewing my capstone submission, and all the best for your assignment.